This presentation is the East Branch Dam case history, where internal migration resulted in a dam safety incident and eventually led to the installation of a cutoff wall to reduce the risk. The objective of this presentation is to identify the key factors and clues about possible vulnerabilities important to evaluating internal migration. You can then apply these same clues as indicators to guide judgment when assigning more and less likely factors and assessing the likelihood of internal migration at other structures. This presentation will cover an overview of the dam, the early observations of seepage, and the risk assessments and dam safety modification that would follow. Let's start with an overview of the dam. East Branch Dam is located about 130 miles northeast of Pittsburgh on the east branch of the Clarion River. The dam is a zoned earth embankment, 184 feet high and 1,725 feet long, with a gated control tower and a concrete line conduit through the right abutment. It was constructed between 1947 and 1952. Here is a typical embankment section. The 184-foot tall embankment has an impervious core flanked by random fill zones. The downstream random fill zone has a rock fill toe underlain by a rock drain. The rock drain was constructed with rock up to 3 cubic feet in size. The filter consisted of a layer of sand and gravel. Borings have revealed that the filter is missing in many areas, which suggests that it likely washed into the drain. The upstream embankment slope is covered with rock protection, with slopes ranging from 2.5 to 1 to 4 to 1. The downstream slope is grass covered with slopes ranging from 2 to 1 to 3 to 1. The spillway is a concrete lined channel in the left abutment with a 250-foot long side channel inlet weir. The spillway is 2,209 feet long and 50 feet wide. The walls and floor are anchored into bedrock. The outlet works consist of a 10-foot diameter, 1,250-foot long concrete lined tunnel through rock in the right abutment, a gated control tower, and a stilling basin. The foundation and abutment rock consists of sandstone, siltstone, and shale with near horizontal bedding. As shown in the photo, the rock is very broken with significant joints and fractures on the abutments due to valley stress relief. Construction of the dam began in June 1947. This is a view looking towards the right abutment and the cutoff trench. The narrow cutoff trench was excavated down the right abutment and a short distance across the valley bottom. This trench extended through overburden and into the underlying bedrock. A concrete grout cap was placed in the bottom of the trench, and drilling and grouting of the right abutment was performed through the grout cap. Very large stress relief fractures are present in the rock, as shown in the photo on the left. This fracture was located very near the incident location. There is also a bench in the abutment in the cutoff trench, as shown on the right, and it may have been the source of differential settlement and embankment cracking. Foundation treatment, particularly on the right abutment, was inadequate by today's standards. It consisted of a grout cap and grouting only on the rock face in the bottom of the cutoff trench. The fine-grained impervious core was placed directly against the highly fractured rock on the sides of the cutoff trench without surface treatment or a filter. Also, the natural overburden was not stripped from the remainder of the right abutment foundation, as would be the standard practice today. The narrow and deep cutoff trench shown here also likely made it difficult to compact fill properly within the trench. The steep sides and abrupt change in slopes can also lead to low confining stress zones, differential settlement, and internal cracking of the embankment. Adding to the potential list of issues, there was a haul road that cut diagonally across the slope of the right abutment. that was originally built for construction of the outlet works. During construction, springs were encountered both upstream and downstream of the dam centerline. Emerging seepage was initially forced upward on the abutment by progressive fill placement. Eventually, drains were placed, which allowed seepage from the springs to exit the foundation. The dam was completed in October of 1952. The first seepage issue occurred at the dam in 1953 at the left abutment. After first filling, very high seepage flows were observed in the left abutment fractured bedrock near the spillway channel. Weirs were constructed to monitor flows that ranged from 1 to 2 CFS. Chemical analysis confirmed the seepage was coming from the reservoir. A grouting program was performed a couple years later using angled borings from the spillway to try to target the fractured rock zone that was found to be the primary seepage path. Although it was determined that the grouting was largely ineffective, no other remediation was performed. The next seepage incident occurred in 1957. On May 8, 1957, the dam tender reported muddy water flowing from the rock drain at the downstream toe of the dam in the original stream channel. He reported that the discoloration had been observed a week earlier, but the flow now appeared to be increasing. On May 9th, a temporary weir was constructed to measure the flow, and an initial reading was taken. By the next morning, flow had increased significantly. A partial drawdown of the reservoir level to 30 feet below summer pool was ordered. Drilling to locate the source of the seepage proceeded during the next 2 weeks. Holes were augured in the embankment with no sign of seepage or voids. Holes were then core drilled along the downstream right abutment contact. Drill water was lost in all 3 abutment holes. However, dye added to the holes did not appear in the seepage at the downstream toe. While drilling focused on the abutment, changes were developing within the embankment. A large rock which had been covering one of the borings was blown off by the air surge from a collapsing void in the embankment. Borings that initially were dry now had water equal to the pool. Rushing water was audible in one of the borings and described as being quite a roar, and dye placed in the boring appeared at the downstream toe in 1 hour. These observations initiated another 20-foot pool drawdown. A grout mixing plant and additional drilling equipment were mobilized by the district, but the Ohio River Division ordered the grouting be delayed while further exploratory drilling continued. On June 10th, over a month after the initial report of muddy flow, one of the drill holes in the embankment encountered a void in the impervious core just above the grout cap. No remedial action was taken, and drilling continued without further incident until the 18th of June, when 2 more holes encountered voids. This finally led to a decision to lower the pool an additional 60 feet. This slide shows the grout plant on the crest. From June until November, repairs consisted of filling the encountered voids with grout and consolidation grouting of the surrounding area of the foundation and embankment. This slide shows the areas that were grouted within the erosion pathway discovered by the borings. Borings just upstream of the downstream rock drain were filled with sand in an attempt to create a filter. Standard grouting on 5-foot centers was not successful as the muddy flow was still present. Large diameter holes were then drilled, filled with gravel, and gravity grouted from the bottom up using the Tremie method. After this, the once muddy flow became clear. Here is a plan view showing the shape of the void in the embankment. And now here is a section view of the shape of the void within the embankment. The volume of the void was estimated to be equal to that of a school bus. There were a lot of negative factors that contributed to the incident, including untreated flaws that existed in the rock foundation, areas where adequate compaction of the embankment materials was likely difficult to achieve, poor geometry and conditions that likely led to zones of low stress, differential settlement and cracking, and unfiltered exits into both the rock foundation and the rock drain. With all these issues at the same location, it is very fortunate that the dam did not fail. The risk assessment started with a screening in 2006. The dam was then classified as high risk. In 2008, Reclamation led a joint risk assessment that resulted in recommendations for interim risk reduction measures and a more detailed baseline risk assessment. Following this risk assessment, a reservoir restriction was implemented, lowering the summer pool 20 feet to elevation 1650 and a winter pool nearly 30 feet to elevation 1623. Additional instrumentation with more frequent monitoring and 24-hour surveillance at the dam, amongst other things, were performed in the interim to reduce the risk. A baseline risk assessment was performed in 2009 and led to the 2010 Dam Safety Modification Study. The Dam Safety Modification Study was completed in 2010 and evaluated the following primary risk drivers: PFM5, internal erosion of the embankment into fractured bedrock at the right abutment; PFM11, internal erosion of the embankment at the interface of the grouted cavity at station 830, the location of the 1957 incident; and PFM8, internal erosion of overburden into the fractured bedrock at the left abutment, with an unfiltered exit into the spillway drainage system or from the outcrop in the vicinity. This study was performed prior to the current terminology and prior to the current event trees used to evaluate different internal erosion processes. Internal erosion is a broad term, and specific mechanisms are now assigned. PFM5 and PFM8 are both internal migration potential failure modes. PFM11 can be considered concentrated leak erosion, internal migration, or some combination thereof, as is often the case when working in karst environments. PFM5 is internal erosion of the embankment into the fractured rock anywhere in the right abutment. PFM11 is in the same area, but postulated as internal erosion of the embankment specifically at the interface of the grouted cavity plug at the location of the 1957 incident. Piezometers in red were found to read pool, including 77-EDB-38, which is downstream of the cutoff trench. This means that the cutoff is largely ineffective. Further downstream, 77-EBD-26 and 77-EBD-28 were dry. This results in a very high gradient between PZ's EBD-38 and EBD-26. Full pool head loss occurs over a very short distance downstream of the cutoff trench. This plot shows how the readings of EBD-38 track with pool, which is very concerning for a piezometer downstream of the dam centerline. It is showing a continuous pathway for water to flow through the foundation, and that the cutoff trench is essentially doing nothing. During construction, springs were encountered both upstream and downstream of the dam centerline. Emerging seepage was initially forced upward on the abutment by progressive fill placement. Eventually, drains were placed, which allowed seepage from the springs to exit the foundation. Left abutment weirs 5, 7, and 10 showed increasing flow trends correlated with pool. This suggests a worsening condition, perhaps the erosion of soil infilling from the karst foundation. Dye tests in the left abutment showed direct connections from borings upstream to unfiltered weirs as shown here. Dye was introduced upstream and then found in the weirs downstream shortly afterwards. Dam safety modification. With a high risk associated with all three of these potential failure modes, PFM11, PFM5, and PFM8, risk reduction actions were considered necessary and justified. The dam safety modification study recommended a full-length, full-depth cutoff wall with supplemental grouting in the right abutment as the selected plan. Here's the section view of the proposed cutoff wall. It addresses the flaw, progression, and breach nodes for all three risk driving potential failure modes. Here is the cutoff wall layout. The grout lines were installed along the same alignment as the cutoff wall. The alignment of the cutoff wall changed in the left abutment due to the spillway. The dam safety modification study originally had the wall cutting across the spillway. A double-line grout curtain with upstream and downstream holes was installed at an inclination of 15 degrees from vertical. The grout lines on the abutments were designed to supplement the cutoff wall for seepage control. The remainder of the grout lines were installed to control slurry losses during cutoff wall panel construction. Here's a photo of the installation of a two-line grout curtain. Cutoff wall construction consisted of a concrete cutoff wall using the panel method along the dam and spillway approach alignment, along with a secant pile encasement wall in the area of the 1957 grouted void. The wall was constructed with overlapping individual primary and secondary panels. Primary panels were 32 inches wide and 10.5 to 27.3 feet in length. Secondary panels were 42 inches wide and are 10.5 feet long. Secondary panels were excavated a minimum of 6 to 10 inches into the adjacent primary panels. Here are some more photos from the cutoff wall construction. On the left is the Bauer Hydro Mill used for cutoff wall panel construction. The tool to clean the sidewalls of the adjacent panel prior to placing concrete in the closure panel is shown in the middle. On the right are the two tremie pipes used to place concrete in the closure panel. Red dye was used in closure panel concrete to aid in evaluating joint quality. Case-drilled shafts were installed to encase the embankment area where the cutoff wall needed to be constructed through the area previously damaged by the 1957 incident. This was done to eliminate the risk of slurry used with the hydromill, possibly initiating erosion in the damaged embankment. An overview of the risk reduction will be discussed by examining an internal erosion migration event tree for the original and modified embankments. Node 1 is the presence of a flaw or open rock defect. The foundation rock is very broken with significant joints and fractures on the abutments due to valley stress relief. Node 2 is the effectiveness of foundation treatment. The core trench was narrow and deep, which made compaction difficult. Steep sides and the abrupt change in the slopes of the trench may have resulted in low confining stress, differential settlement, and internal cracking of the fill. There was no head loss measured at piezometers in the downstream edge of the cutoff trench, which shows the cutoff trench to be ineffective. Outside of the core trench, the embankment was founded on overburden with no cutoff or grouting. Node 3 is initiation. Poor compaction was likely at the right abutment interface, and there was potentially internally unstable soil in the foundation. Very high gradient was measured downstream of the cutoff trench. Node 4 is continuation. There is an inadequate filter transition between the overburden and rock drain. Borings revealed that the filter transition material is missing in many areas and likely washed through the drain. Node 5 considers the potential for clogging, but considering the large-scale defects in the rock, clogging was very unlikely. In the post-remediation condition, the concrete wall fully cuts off and eliminates the failure path. Where there is cracking in the wall, the cracks were less than 1/4 of an inch, which would be very likely to clog given the sandy gradation of the embankment material. For potential pathways beneath the wall, the flow path would have to go 90 feet down to get around the bottom of the wall, and it would have to progress through much more competent rock. As such, this pathway has significantly lower risk. The primary references are provided here for more details on East Branch Dam and its long history. This concludes the East Branch Dam case history presentation.